Hey guys, just letting you know, I apparently forgot to click that one button that starts the live stream, but the live stream is now running. So I believe the live stream is now running. Okay, let's do a quick latency check. If you can hear me, please wave. And okay, we got it. Sorry about that. So when this live stream started, I actually forgot to press the button that broadcasted on YouTube. But glad to see that we're all here, and happy Monday to you. This is the last week of our class at Carnegie Mellon, and so we're going to tie up a bunch of different ideas that we had. So the first one is about this theorem which we just had, which is the Franco-Wilson theorem, which talks about how if you have a bunch of subsets of 1 up to n, and if you have some intersection properties, then you can't have too many of them. So at first it's kind of cute. It's like, well, nice fact, but could you use it for anything useful? And the answer is yes. So the first application of this is to explicit constructions of Ramsey graphs. What do I mean by that? Just a second. Save. So a Ramsey graph is a graph, or it's a two-coloring of the edges of the complete graph. Either way is fine to think of it. I guess we can think of it as a graph, right? So Ramsey graph constructions. So these are constructions, and so the purpose of this construction is to make a graph which has n vertices and not so big of a clique, or not so big of an independent set. So these are n vertex graphs with maximum clique size and the maximum independent set size, all small. So now what would that mean? Well, we already know that if we use a random construction and we just say we take our n vertices and every single edge appears independently with probability 1/2, then it will work well. You'll be able to get such that all of these cliques and independent sets are of size at most log base 2 of n. So the random construction, random gives max clique and independent set sizes of at most order of log base 2 of n. Well, it's log n is all I need to say because it's order of magnitude, so it doesn't matter what the base is. Now, we can also think of it another way. The other way to think of this is that if you are going to say that your biggest clique and the biggest independent set is no bigger than t, then we're able to make this graph with no clique of size t, no independent set of size t, and that graph has a lot of vertices. That's the other way to think of it. Or there exists a graph with all cliques of size at most t, all independent sets of size at most t, and it has a lot of edges. And has a lot of vertices. And the number of vertices is of order, it was like square root of 2 to the power t. So that's exponential in size, and we already know that you can't have one which satisfies these properties, meaning no big clique, no big independent set, and has like 4 to the t many vertices. So now the question is, that's nice, this is a random construction. Can you find a construction that's not random? And people tried for very long, and in fact, for a very long time, the only construction people knew, really, was something that was t here, and about t squared there. The about t squared there was just take a bunch of cliques of size t minus 1, and we saw that. A bunch of cliques of t minus 1 vertices, we saw that construction. And you put all these together, t minus 1 of these cliques, you get about t minus 1 squared vertices, which is nothing compared to this. And that was actually the best explicit construction for a very long time, until around the 70s, I believe, 60s or 70s. And there was a construction by somebody named Nagy, N-A-G-Y. And Nagy observed that you can do something quite different. We can go and try to make this kind of an object where there's bounded size cliques, bounded size independent sets, but you can use the vertices to be subsets. I mean, you just take subsets of a big set and let those correspond to vertices. And the particular construction that Nagy had in mind was that the vertices are 3-element subsets. I'll call it 3 sets. 3-element subsets of the numbers 1 through, I guess we can call it t. Now, if you do this, we have to decide on some reasonable way to decide which 2 sets are adjacent and which 2 sets are not adjacent. And one of the ways that could work is you could say the edges are between sets which have intersection size exactly equal to 1. So this is something you could do. And it turns out that you can use some relatively elementary set theory type arguments. And you don't need any fancy technology, but if you do something like this, you can go and show that the biggest clique and the biggest independent set are each at most t plus 1. So that's a bound that we can show. I won't bother to actually show this here because we're about to show something stronger. You can show, and this is an easy exercise, you can show that the maximum, well, let's say all cliques and independent sets have size at most t plus 1. And that's an exercise if you want to play with that. The reason I'm not going to prove this is because I'm going to prove something much stronger. But when you look at this already, what do you see? You see that the number of vertices in this graph is about cubic in t. So this is already better than the quadratic explicit construction. So again, what this purpose of this section today is explicit constructions of Ramsey graphs. So we want an explicit construction with no randomness, where there's no clique that's very big, no independent set that's very big, but yet a lot of vertices. And we want it explicitly, not randomly. And explicitly before, you could get like t minus 1 squared, and this you'll get about t choose 3, which is cubic in t. But it turns out you can actually get more, and that's satisfying because we should be able to get exponentially many, although to this day we still don't know how to get exponentially many. But the first big breakthrough that went beyond these polynomial type bounds was a construction by Franco and Wilson. So Franco and Wilson, the same two people whose names were on that theorem I just talked about, Franco and Wilson had a construction that was basically an extension of this with bigger primes. Primes. Well, you see, the Franco-Wilson theorem had primes deep inside it because we did a lot of work over FP. In fact, one of the important theorems in this Franco-Wilson group of theorems, one of the important theorems was discussing what happens when I have intersection sizes modulo P. And you'll see that that's a very, very important point. So there will be a prime P. So let P be a prime. And the goal here is that we're going to be talking about some subsets of, we'll be saying the vertices are some subsets of an n set. So what should n be? Well, these are some choices. We'll have to choose some parameters. But let's decide the n later. So let n equal something. And what we'll do is the vertices are the p element subsets. I'll call them p sets of square bracket n. Okay, so now here's a question. Because we just learned some stuff about Franco-Wilson, what might I be able to use for the edges? And the inspiration comes from here. You see, this is also where we're about to find out a good choice of n. So the n, by the way, is not going to be huge. The n's not going to be exponential in p. The n's also not just going to be p. The n's going to be something that depends on p in a certain polynomial way. But what I want is I want to know what kind of Franco-Wilson theorem could I use. I will put that somehow the edges are going to be between sets with an intersection size of a certain form. So we'll say this. The edges are between sets with intersection size well, there's going to be some set. So in some set. I won't close the bracket yet because this is a fairly long bracket. But now what could be useful? So I'm going to have a p involved. I'm going to take, oh wait, actually let me take that back. We don't want p sets. That's actually very important. I don't want that the vertices are p element subsets. I actually will want that the vertices are subsets of square bracket n whose size is exactly p squared minus 1. That's actually going to be very important. So let me take that back. These are subsets of square root n, subsets of square bracket n of size p squared minus 1. And this is a very carefully chosen p squared minus 1. So does anyone have an idea of like, what might I be able to use? I want to use some Frankel-Wilson type stuff. Let's remind what we know from Frankel-Wilson theorem. Frankel-Wilson theorem says if I have a bunch of sets, I've got two versions of this theorem. One version of the theorem is if I have a bunch of residues modulo p that all of my intersections lie in, but my set sizes themselves are not in that residue class mod p, then I have at most some number of sets. You know what? I think it would be most useful if maybe I write that on the next screen, because maybe not everybody was here during that particular class, and I'll just write this down to remind what we know. So we have a few theorems. One theorem was that if I have a bunch of subsets, so if, let's just say given a family of subsets of square bracket n, and here I'm calling them L intersecting mod p, L intersecting mod p, where the size of L is equal to S. Given this, there are, at most, and the bound was something like n choose 0 plus n choose 1 plus n choose S. And just to remember what this L intersecting mod p, when it was mod p, what we had was that any two different sets intersect at size in this residue class in L, and any one set has size not in the residue class in L. So that's what L intersecting mod p meant. And like what we saw from this particular construction was this was roughly speaking corresponding to an almost best possible situation where you had L being 0, 1, 2, 3 up to S minus 1, and you just took all the sets of size S. That would be one way of getting something like this. That was one theorem. And of course, there's this extra stuff in the beginning. But those are lower order terms that we don't need to worry too much about anyway. And the other theorem that we want to use was that if I am given the family of subsets, which is just L intersecting, then the whole thing holds true. And L intersecting, that does not require that the set size itself is not inside L. So this thing is just any two different sets intersect at size, which is in L, and no other condition. Okay, so this is the pair of theorems I can use. How could that be useful? So now I know that I have something which is modulo p, but the thing modulo p, my set sizes can't be in L. Does anyone have anything clever to suggest here? So the idea is that we want to make our vertices to be subsets. We want to do something about like not too many intersections. You can already see how this is feeling, sort of like cliques and independent sets. We'll in fact use both of these theorems. One of them we'll use for the cliques, one we'll use for the independent sets. I saw Bryce had a hand up. Uh-oh, maybe my audio is not through. But that's strange. I heard you guys earlier. Bryce, did you say something? Let me quickly double check my audio. I think you said something, and I think what this means is I must not be able to hear you? No, but that's there. Oh no. Can everyone else, can someone else just like, oh, I hear you. I can hear you. I can hear you guys. So I just heard Ariel, I heard somebody else too. So Bryce, I'm wondering if your thing is not working.
I think Bryce's mic is not working.
Oh no, so Bryce's mic is not working. Okay, well, actually, here's what I'll say. If you post something into the chat, I can also read. So, both are fine. So, I mean, at this point, if maybe Bryce is going to type something into the chat, also we're trying to think, what could I use? Let me just start writing down construction. What should the construction be? Construction, what we'll do is the vertices are subsets of square bracket n of size exactly equal to p squared minus 1. So what can we do? Yes, force the intersections to not be minus 1 mod p. Let's try that. Okay, so this is, by the way, an excellent idea. It's because I already know that all of my subsets are congruent to minus 1 mod p. That's why this is chosen. And so I could put myself to satisfy this condition up here if I just made the set L to be all the residues except minus 1. Let's try that. Okay, so what we'll do is we'll let L be the set of residues 0, 1, 2, up until p minus 2. These are residues, mod p. Okay, so in this case, let's go and see what happens if I say make an edge to be, I mean, actually it doesn't matter whether you call them edges or not edges, but I see that what Bryce is suggesting is that if the intersection size is in here, call those edges, and that would be perfectly reasonable. So we say that an edge means that intersection size is in L mod p. Okay, so now when I do this, I automatically am in the first situation in the Franco-Wilson result. In the first situation of the Franco-Wilson result, what I just found out is I have a set L. The size of the set L is exactly p minus 1. So what I find here is the size of the set L is equal to p minus 1. That's my S that I'm going to play with. And now I have all of these edges, and so the most number of things in my clique, right? So now I can bound my clique. The biggest clique I have, by the Franco-Wilson result, has something to do with this S. So the first Franco-Wilson theorem let's give these numbers. Theorem 1 and Theorem 2. That was Theorem 1. This is Theorem 2. Theorem 1 is going to tell me that the maximum clique has size at most is just going to be the n choose 0 plus all the way up until n choose p minus 1. Okay? So, by the way, how you should think of this is that if I went and chose my n to be, somewhat big, this is quite nice, because this is going to be something which, if n is bigger than p, this is like around n to the p-ish order of magnitude. You can think of n being a lot bigger than p, growing a lot faster than p, in which case the beginning terms are not so important, and n choose p is sort of like n to the power p. Okay, so that's pretty good. We have an n to the power p bound. Why is that pretty good? The reason that's pretty good is because the number of sets that I have is p squared minus 1. Is sets of size p squared minus 1, which is, the number of vertices I have is very big. The number of vertices is n choose p squared-ish, and if the biggest clique is n choose p-ish, then I might have something which is a better bound. That's the insight. But we have to use Theorem 2 also to go and find out, well, what's the size of the largest independent set? But here's why it was p squared minus 1. The reason why it was p squared minus 1 is what's an independent set? An independent set means that the intersection size happens to be minus 1 mod p. But that's why we have p squared minus 1. There's like p of those choices. Do you see? So what I can do is for theorem number 2, what I have here is that the independent set is a family where all intersection sizes happen to be, well, whatever is left. All the things which are minus 1 mod p. And so all intersection sizes are in the set. Minus 1 mod p starts from p minus 1, and then it's 2p minus 1, all the way to p squared minus 1. And here, there are p of these. Actually, I don't even need to worry about p squared minus 1. That's going to be kind of nice and symmetric. There's no way I'm going to get intersection size of exactly p squared minus 1 because my sets are of size p squared anyway. P squared minus 1 anyway, so I can strike that one off. And what I see here is I see that there are p minus 1 of them. And with that, you see the power of the Franco-Wilson theorem. It's because on the one side, in order to use the modular one, then you just need to make sure that your set size itself is not in that residue class. Otherwise, you can just use the other version, which you don't have the restriction of the set size, like avoiding the residue class, but you still get a bound. And when you look at this, you should also see that's why the modular version is so interesting. The modular version effectively let us do the non-modular version about p times as effectively. Does that make sense to people? It's like if I tried to use the non-modular version to do the modular component, then I would actually have to strike out like p squared minus p-ish things. And then I would just get a huge bound. I would get this sum, which is n choose 0, n choose 1, all the way to n choose something very huge, which is already quadratic in p. So that's the point. And when you put these two together, we have the same bound. So now what we found out is that if I happen to use this p squared minus 1 as the size of my set, then the biggest clique and the biggest independent set has size at most asymptotically about n choose p minus 1. So that's going to be the asymptotic we're playing with. Okay? So what do we have now? We got the number of vertices is about n choose, well, not about, it's equal to n choose p squared minus 1. And we got that the number of edges, the maximum clique and independent size, max clique, and the max independent set, both of these are at most, it's of order of magnitude, so I'll write ish, at most order of magnitude n choose p minus 1. Let's just write n choose p, okay? So this, by the way, is going to be about n choose p squared. Okay, so now we want to know approximately what to pick for n. Once you look at this, you say, oh, I want to make the p squared easier for you guys to see. This is n choose p squared. Once you look at this, you say, my goal is to try to make this so that these numbers are interesting. Interesting means that then this number is getting bigger, this max clique, max independent set is getting bigger, but I want the other number to be really, really big compared to that. That's what we're trying to do. So now we need to know approximately, how big are these things? So if I'm eventually going to pick my n to be much bigger than p, I'm going to just say approximately, how we can maybe think of this. So this n choose p squared, this is going to be, when n is very big compared to p, this is going to be like approximately n to the power p squared. Of course, it will be divided by this p squared factorial, but if n is really, really big, this is the main part. And this thing here is approximately n to the power p. Now, I would like that the n to the power p is very big compared to the other one. And it turns out that if you choose n to be p cubed, this works pretty well. So let's see what happens if you choose p cubed. We don't want to pick p squared. The way to think of this is you don't want to pick p squared, because if you chose p squared, if n is like p squared, the top one is very, very small. P cubed is the first place that you start to make progress. So let's try n equals to p cubed. And you can optimize this, but it turns out there's not much better that you can do. If you try n is about p cubed, then how do I compare these things? Actually, let me put the n equals p cubed farther to the right, because I want to write exponential notation. Let's try n to be p cubed. Then what you do is you'd say this particular n to the power p squared, that's equal to e to the power p squared log n. And log n is log p cubed, so I get a 3 log p. And this n to the power p is e to the power p times log n, and log n is again 3 log p, so 3p log p. The goal of this construction is just to show that we can make something where if I want to say this bottom number, the maximum clique, maximum independent set, I want to say that if this thing was t, then the thing up there happens to be bigger than any polynomial of t. Right, because we saw previously that there was a way to get, if the second one was t, we could get like t squared. There was a claim you could get like t cubed. And the point is, with this choice, with a p that's moving, if the bottom thing is like a t, the top thing is going to be of order bigger than just any power of t. But the way to do that is to say, let's just call this t. And that's why this particular way of parametrizing makes sense. If you call this thing t, then the top thing is t to the power p. Now, the goal is to show that the p is actually something that grows with t. If I can show that as t goes to infinity, p goes to infinity, then I have a family of constructions of these Ramsey graphs where there's no clique or independent set of size t, but also the number of vertices is growing faster than any polynomial of t. And the way to do that is just to go and say, well, I just need to show that if I have this particular relationship, then as t grows, then p grows. But that's obvious, because as t grows, you better have p grow, right? If you just look at this particular relation at the bottom, as t goes to infinity, given that there's this relationship, p also goes to infinity. So from this particular one, what I can see is that limit as t goes to infinity of p is also equal to infinity. And so that's how I know that this is growing faster than any particular power of t. Did that make sense to people? Like, if you think about this, we had seen constructions where you have a t here and a t squared there. I claimed there was a construction that was a t here and a t cubed there. But this is much better. This is saying that as you have a t here, you have something that's growing faster and faster. How much faster? Unfortunately, it's not very fast. If you want to go and reverse this particular relationship, if you want to reverse the relationship, then roughly speaking, p is going to be of order sort of logarithmic into t, if you can look at this, because, if I take log of both sides, I get that 3p log p has to be log t. And this log p is a smaller order term. Like, strictly speaking, we could work that one out too. But this p was going to be something with a log t inside it. And so it will grow very slowly, but it will grow. Okay, so that's this. Now I also said, I promised you that this naggy thing of the intersection sizes being these intersection sizes being 1. I told you I don't need to go and prove that. Well, the reason is because actually that logic is in here already. So if I want to look at this particular case where I have these 3 sets, which is sets of size 3, that's just a p equals 2 case. P squared minus 1 is 3. And over here, we're saying that we are going to talk about whether the intersection size is exactly 1 or not. That happens to be p minus 1. So here, that happens to be the complement of this particular construction. So okay, so we just saw that too. So this finishes this Franco-Wilson construction. This finishes this Franco-Wilson construction of these explicit Ramsey graphs. Are there any questions on this piece? So this is one of these nice applications. Let me go here and flip this. I want to see how far I can get today. So this is one of these applications, and they're actually quite surprising that you can use this intersections of sets to go and prove some of these bounds that people have been trying quite hard to go and get an explicit construction for. Then let's go on. The next thing that I want to do is something that's related to chromatic numbers, but it's going to turn out that this Franco-Wilson result is again useful for that. So let's see what we do. The next thing that we want to discuss, is the chromatic number of the unit distance graph. So this is let's use a white for the chromatic number. Anyway, chromatic number of the unit distance graph. So what this is there's an infinite graph. The infinite graph is all of the points that are in R2, all the points in the plane, and you connect any 2 of the points if those 2 points happen to have a distance exactly 1. So chromatic number of unit distance graph, all we do is we take the vertices is all of R2, that's a set, and you have a pair, an edge. An edge is equal to between any pair of vertices at distance exactly equal to 1. Now this problem is a very hard problem. Nobody knows the answer. In fact, this happens to be, I believe it has a $1,000 prize if you solve it. Although actually if you solve it, the $1,000 is not the motivation. There are easier ways to earn $1,000. But the question is, what is the chromatic number of this graph? And actually today, all we know is that this graph has a chromatic number somewhere between 5 and 7. There was actually one of these breakthroughs relatively recently where somebody came up with a subgraph of these points in R2 which could not be colored with 4 colors. So now we know the chromatic number is between 5 and 7, but we don't know the answer. So we happen to know that the chromatic number is somewhere between 5 and 7. And if you want to prove the lower bound happens to be something where you just have to go and find a particular subgraph. Okay, it sounds easier. It's actually very hard to do, but you go and find some particular subgraph, and if you can find a particular finite set of points in the plane, which happens to require at least 5 colors to color, then you're here. Right, so this lower bound happens to be from find an explicit subset. Finite subset will do. Of points in R2 needing many colors. I mean, that basically reduces this problem into like a normal finite graph problem. The other side is one where you just go and find a coloring and you use it. So, there's a way to color all of these points. It has something to do with like a hexagonal grid. If you can think about the fact that why is this 7 relevant, it's because I can go and draw a bunch of hexagons. So let's go here. The reason why you can prove that is you can sort of tile the plane with these hexagons. And if you choose the hexagons right, if you choose the size of the hexagons right, then it turns out that as long as you give the hexagons a valid coloring meaning color the vertices inside the hexagons, I'll just draw it like this. If you use a particular valid coloring where every single, wherever you have a hexagon, you don't have the same color right next to it. I don't have enough colors in my palette here to draw all of them. But it's just that if you can draw all of these hexagons and you make it so that it's a legit coloring out of hexagons, then because the hexagons fill up all of this space, you can go and make sure that there's no 2 points which are of distance exactly 1, which are right next to each other. You'll find no 2 points with distance exactly 1, which happen to be of the same color. You just go and make sure that these hexagons are small enough. Okay? So you can do such a thing. You can color this, and why does the 7 come about? It's because if I want to know the chromatic number of this hexagon graph, well, every single vertex has a degree of 6. And so even if I use the dumb, greedy coloring, I could actually go and color this with 7 colors. So that's how you get both bounds. Unfortunately, this problem has been wide open and somehow seems hopeless. So what we always do as mathematicians is, if you can't solve this problem, make a harder problem and try to solve that one instead. And so the harder problem happens to be, what if we try different dimensions, right? Let's just go and see what happens if I go and not say R2, let's go and see what it is in RD. Okay, question is too hard. Too hard, we give up for now, and we go and say, here, what is the chromatic number of R to the power D? Okay, now on the one hand, you can go and make some construction of a graph which requires at least some number of colors. Let's start with that. Let's get some audience participation too. Let's start with an observation where the chromatic number of RD is at least something. Anyone have an observation? So it can be something depending on D. And the way you'd make this, the way you'd prove this is you'd say, here is a bunch of points in R to the D, and there's a graph, the unit distance graph on them. That's a normal graph theoretic graph, and that graph has a chromatic number of at least something. You can give a bound. The bound doesn't have to be super amazing, but there is a way to make a bound that goes to infinity as D grows. Does anyone know a particular good collection of points? Philip.
The unit simplex will be a KD plus 1.
Yes. That's D plus 1 by just taking the unit simplex. It's like if I have an equilateral triangle in 3D or a tetrahedron, equilateral triangle in 2D or a tetrahedron in 3D. So what this is by considering the unit simplex. And the unit simplex is triangle in R2 and tetrahedron in R3. Sorry, these are not just, this like the unit, the equilateral triangle or the, I guess, equilateral tetrahedron or something like that in R3. And you always will get one more than the dimension. So we can do this. Well, I guess we have another question, which is how about the upper bound? So let's leave that as a lower bound right now. And let's just have some fun thinking about upper bounds for a bit. Anyone have any upper bounds? They don't have to be great. Again, let's start from anything. I want a finite upper bound, where finite means that if you give me a D, some finite number spits out. And you can start even motivated by this hexagonal filling. That is actually one not bad way to do this. Yes, Tingwei.
Like if you partition it into some small cubes, maybe the length of the diagonal is at most 1. And you can color it by maybe 3 to the D or 5 to the D colors.
Okay, let's try partitioning the unit cube. The unit cube is a good idea, so we're going to take the unit cube. And the unit cube has distance 1 on each side. And you want to partition this into some tiny, tiny cubes where each cube has diameter less than 1. Always we want the diameter to be strictly less than 1. That's the same principle as the hexagon coloring. Okay, so we'll take this unit cube, and it happens to be partitioned into lots of tiny cubes where each tiny cube has a diameter less than 1. Into small cubes of diameter strictly less than 1. And what we'll do is, just like inside this particular unit cube, let's go and just find some coloring that's valid. Coloring that's valid, actually in this case, we're just going to color everything with a different color. We're going to get some bound to begin with. So partition this into all of these tiny cubes, and each of those cubes, all the points inside get a unique color. Each cube interior gets own color. Now the reason why this is useful is because we're then going to take this as a unit and use this unit to tile space. And if you use this unit to tile space, because I have a distance of 1 along this side, I guess I probably need to be specific and say, on this particular unit cube, I'll include like the bottoms, I'll include all of the lower endpoints, and I'll not include the upper endpoints, right? So this unit cube happens to be something like, maybe if I want to draw it this way, happens to be something like square bracket 0, 1, open bracket to the power d. What I mean is that somehow I'm not including the upper endpoints, and that just lets me actually partition space into translates of this cube. And because of the endpoint considerations, I don't ever have to worry about what happens between points in different cubes. Any points in different cubes have a distance which is already strictly bigger than 1. Right? So in that, wait, is that the case? No, that's not the case. That's annoying. Actually, if I take a point here and another point there, they could potentially be the same color. And in fact, they are the same color. So I don't like this. No, let's go and adjust this very slightly. I'm going to say, I don't want the 1. I would like 1.01. Something just big enough, okay? But it's not going to hurt because we're doing asymptotics anyway. So I don't like this. Let's use 1.01, or I'll just write 1.1. But all that matters is it's bigger than 1. Oh, 1.1 is convenient. I can write it that way too. Okay. So 1.1, 1.1, and the purpose of this is that I'll never have to worry about 2 points in different cubes because they'll be too far apart. And now I go and see how do I do this? Well, if I want all of my cubes to have diameter less than 1, exactly as Tingwei said, the thing to worry about is the long diagonal. So if I look at the long diagonal on a cube, if you're in d dimensions, the long diagonal is square root of d times the side length. And so if I want to have these cubes of diameter less than 1, actually, in this case, I'm okay by using this like half open, half closed, because then I don't have to worry about 2 points which are on opposite sides. And so this particular cube, this has side length equal to 1 over square root of d. Because if each of those cubes has, and let's not write less than 1, let's write less than or equal to 1. I can do these cubes with diameter less than or equal to 1 because I will not be able to take 1 point and the diametrically opposite point in the same color. That's already the next color. And it happens that the diagonal is square root of d times 1 of those side lengths. So I now have this as 1 over square root of d. And if I do this, if each one gets its own color, then the number of colors I use, I get, well, it's square root of d to the power d colors. Now, Tingwei was hoping to get something like 3 to the d or 5 to the d. And it does turn out that you can improve this bound, and you can actually get an exponential bound instead. So this is not quite exponential. Of course, it has an exponential in it, but what I mean is it's not a pure exponential of something to the d, which would be nice. So the next step is to go and is to make some other argument that can also get an exponential bound. Now, the best argument I know to do this is not very explicit. This is related to coding theory. Like there's somehow in coding theory, what you can sometimes do is you can use a greedy algorithm, and you can go and try to put down patches of color, Like if you can think of what we're doing here, this is actually very related to error correcting codes. If you ever took any class on those, this has something to do with finding a way to pick a bunch of points so you cover everything. How do you cover everything? Well, one of the most like sneaky tricks in this world, but especially inspired by error correcting codes, is the way you do it. Is you say, let's suppose that I went and took a maximal. Let's go and take a maximal collection of points, such that the points are all at least a certain distance apart. That's a funny thing to do. I'm trying to put down all these patches of color, but it turns out that what you want to do is let's find a maximal collection of points where all of the points are at least half apart. I believe that's exactly what I want. Yes, that's what I want. Okay? So to get another construction, here's another upper bound. Better upper bound. What we do is we take a maximal collection of points in R to the D where every pair of points is at distance at least 1/2. Now, what does that have to do with what we're trying to achieve? We're trying to find some way of coloring. So we need to find some way of coloring all of these points all throughout R to the D. This is sort of like a post office distribution. We're sort of saying here's a bunch of post offices, or here's a bunch of points, and what we're going to do is each of those points is going to get a color, and that color is going to be used by whoever is closest to it. So there's two steps. The first is to show that, well, it's a couple of steps. First is that this exists. The reason this exists, even though R to the D is infinite, is because it's a maximal collection. And so maximal is just like a union of sets. So the idea is if I have any increasing chain of these collections of points in R to the D, which has this property, increasing chain means that here's a bunch of points, here's another bunch of points which contains all of the other one. I can union my way all the way up, and I get another one. Does that make sense? So it's like somehow if I just want to find this maximal collection, this exists. The maximal collection is just the union of a chain all the way up. So we can have this maximal collection. This is some infinite set. And now we're going to have an infinite set. Our goal is that this infinite set, we're going to color each of those vertices in some way. And after we're done coloring each of those vertices in some way, we're going to color the other vertices based on who they're closest to. And that's going to give us a valid coloring. And then the only game is going to be to show that I can color those vertices without using too many colors. So the goal, strategy, what I'll do is you'll make another graph. Make another graph. With those vertices, those as vertices, and somehow we'll put distance, we'll use the distance between them. We'll connect them if they could potentially create 2 points which are at too close of a distance. Where adjacent, if points that see those as their closest point could have distance equal to 1. And we'll make this graph, we'll try to color it, show that this graph has a low chromatic number. Show this has low chromatic number. And then you go and just color every point in RD based on who is the closest. Color each point in RD based on who is closest. So you just take the color that's the closest. So why is this interesting? Well, I've got all of these points of distance. This is like some maximal collection of all these points with distance at least 1/2. Okay. Now what happens? Well, I guess I have to go and find out just this piece here. Because, you can always put this thing down. Oh yeah, if there's a tie, just pick any one of them. That's not important. So now let's just figure out what I can do for this pink line. The pink line is the important one. I just need to know, what's my maximum degree? I need to say that somehow if I have a point, one of these points in my special set, as long as I can show there aren't that many other points nearby, then that would be great, right? If I can show there aren't that many points nearby that I need to worry about, then I'm done already, because I'll just use greedy coloring for the pink part. And this already should intuitively make sense, because if I imagine that I have a point, so I have a point here, which is one of my points inside, I'll put a little circle. This is one of my points inside my special set. My question is, how many other points do I need to worry about? Obviously, I don't have to go out to a radius of 1,000,000. Do you know what I mean? It's like some triangle inequality is going to come in. It's like I'm here, and how many other points would I ever need to worry about anyway? Well, it so happens that I've put it so that I've made a maximum, I've made this maximal set here, right? So I guess the way to think of this is, if I have a point here, and if I have another point for whom the other point is associated with this one, meaning it's going to acquire the same color. Here's another point which is going to acquire the same color, meaning that this thing thought it was closest. That's unreadable. I'm going to write it bigger. This other point thought the circled point was the closest, okay? I need to know who else do I need to worry about. Let's draw another one. Here's a yellow. Do I need to worry about this point? Well, I might need to worry about it if there's somebody else who thought it was the closest. Okay, so I'm trying to say, as long as these 2 points that thought they were the closest, as long as those 2 points have a distance of 1, potentially have a distance of 1, then I need to worry about it. Actually, once you see that I drew it this way, you see that probably these are not the way I need to worry about. It's not that these 2 circled points are worrying about each other because there's some point farther away over here and farther away over there that think the distance is 1. In fact, the worst case is when these other points that think it's the closest are on the other side. So let's just go and flip that. Here's what I'll do. I'll just reverse those arrows. Now I circle the other way around. Circle that one. Reverse the arrows. Okay, so my situation now is I'm sort of wondering, from the point of view of this circled point, how far away do I need to worry? Well, you can already see a triangle inequality starting to come to play, because what's going on is that I know that the distance between these uncircled points is exactly 1. And the reason the distance is exactly 1 is because that's what I'm worrying about. I'm worrying like this particular special point in my maximal set and this other special point in my maximal set, could their colors influence each other in the sense that do I need to worry at all what the 2 colors are? If I need to worry, I want to choose different colors for them. And I would have to worry if you could potentially have a distance exactly 1. Now here's the important thing. Can anyone tell me an upper bound on that distance? That's an important part of how we made the definition. There's a claim that this distance cannot be too big. Does anyone know why? It has to do with the construction.
It can be greater than half for sure.
Yes, it cannot be bigger than half, because if this distance was strictly bigger than half, then, just a second, how should I say that? If this distance is strictly bigger than half, then this point is distance bigger than half from everything else in the whole set. So I should just add this one to the set, right? The point is that we had a maximal collection of points, which has the property that all of them are separated by at least half. If there exists any point whose nearest thing has distance bigger equal half, well, then you should have added it to it. You should have added it to the set. So that very first piece, the very first piece tells me that this is actually strictly less than half, because otherwise I could have added the point. The strict is not important here, but I'll just write it. Strictly less than half. Okay, so now I know that for each of my points, I only need to worry about other points which are distance at most 2 away. So now I just have to say, what's the maximum degree of this circled point graph? In the circled point graph, now what I'm going to do is I'm simply going to connect any 2 of the points whose distance is less than or equal to 2. Okay? So again, continuing, we had this maximal collection of points in R to the D with all pairs at distance bigger or equal 1/2. Now what we found out is that if you take any particular point, we'll make a graph. The graph we'll make is we'll connect them if the distance is less than 2. And now I'd like to show that for every one of these points, there's at most some number of them who has distance less than 2. How could this be done? Well, the way that this can be done is by using, again, the property of the fact that all of the pairs are distance bigger or equal 1/2. In fact, this becomes a sphere packing bound. So the question is now, how many other points that were picked, how many other points picked can be distance less than 2 away? And the answer is you take a sphere. This is a sphere around my point that I've picked. The sphere, I don't want to make it to have a distance, I don't want to make it to have a diameter of 2. I'm going to put a diameter of 2 1/4. Why a diameter of 2 1/4? The reason is because I now want to know how many other circled points there might be. So I've got some other circled points in there. I probably shouldn't have circled them because I'm about to circle them again. But I have all these circled points. The circled points are at least half apart. And since they're at least half apart, I can go and make balls around them. And each of these balls has a radius of 1/4. These are disjoint. We're using a volume argument now. Okay, so I just drew a bunch of balls. Each of these balls has radius 1/4, and they're all disjoint. Okay, so now I have an upper bound, right? So the point is, how many of these circled points could I have here? Oh, why did I go to 2 1/4? The reason I went to 2 1/4 is so that they're all contained inside as well. So I have just a volume argument. The volume argument is, how many balls of radius 1/4 could I possibly put to be disjoint inside a ball of radius 2 1/4? And you don't even need to know the 4/3 pi r cubed. You just need to know that volume is cubic in radius. So the maximum number you could have is at most 2 1/4 divided by 1/4 cubed, right? So don't need any formula. So answer is at most 2 1/4 is 9 over 4 over 1 over 4, and we cube it. And that happens to be 9 cubed, 729. Okay, great. Wait, something's wrong. Not cubed. Why am I cubing? It's d, raised to the power d. That's good. And the reason that's good is because I was like, wait, but I do know the formula for a volume of a ball. It's just 4/3 pi r cubed. But I was like, there's something in here where you can avoid doing something harder. And I actually don't remember the formula for the d-dimensional ball. The d-dimensional ball is some nonsense. But this happens to be just 9 to the power d. Hooray! So once I have that, now I know that the recipe for coloring is you first take this maximal collection. It exists somewhere. Okay, this is a very existential type proof. This exists somehow. You can put down this huge maximal infinite collection. And by the way, every single one of these points has maximum degree at most 9 to the power d. So therefore, there's a coloring of these circled points with at most 9 to the power d plus 1 many colors. You use those as your colors, and you have it. And that happens to be your coloring of the d-dimensional space. So today, that will take us to the end for today. We managed to find out that there is indeed one of these colorings. And yes, there's one of these colorings of exponentially many colors. The lower bound we had was d plus 1. And so where we pick up tomorrow is we will try to put squeeze this closer together. Are there any questions?
By squeeze them together, you improve the constant, right?
Oh, well, it's not just improving the constant. Our lower bound is d plus 1. Our upper bound is 9 to the power d. So those are quite far apart. And squeeze together, indeed, it just means improve the bound. So we actually cannot simply use either of the bounds. I just mean prove another bound. However, the reason I wanted to do this is because it turns out that some of the work we did is still useful. So I don't have to give it away. We'll see it next time. Any other questions? If no more questions, then I'll see you all on Wednesday.